again. Zoom in a little bit more. All right, maybe a little bit. So our table looks something like this. Let's see if we get everything in the same picture. We'll worry about these other things here in a second, but this is values of specific heat right here, okay? How does this equation work? Well, it tells us the amount of heat you need to heat up some object M by some temperature change, okay? And then the specific heat shows up right here. Specific heat C is different for different materials, and in general, different materials require different amounts of energy to change their temperature. So let's talk about two of these temperatures here. Let's talk about iron. So suppose I have some iron, and suppose I have some, what's iron close to? Aluminum has almost double the value for specific heat, right? So let's say next to this I have a piece of aluminum, right? And let's say that both of them have a temperature of like 20 degrees Celsius. So let's say both of them have an initial temperature that's equal to 20 degrees Celsius. All right. So what does it mean that aluminum has a specific heat of 910? This is in joules per kilogram times Kelvin. The Kelvin's in the denominator too. Yeah. So aluminum has 910. And iron has 470. So what does that mean? I think the Kelvin can be replaced with degrees Celsius here too, because it's a delta T, right? So let's say that I add, I don't know, 1,000 joules of heat to this right here. That's not enough probably, right? Let's say that I add 10,000 joules of heat to this guy right here. And we do the same thing to this guy right here. Which one of them is going to be hotter? The iron. Why do you say that? From this equation, the change in temperature is going to be equal to the amount of heat that you put in, which is going to be the same for both objects. Oh, and let me say they both have the same mass. So let's say this mass is 1 kg, and let's say this mass is also 1 kg. So they both have 1 kilogram. So you end up dividing by the mass, and you divide by the specific heat, right? Lower C value, that's a really good way of putting it. A lower C value, a lower specific heat, means less energy needed to get hotter. Less energy needed to get hotter, exactly. Less energy needed to get hotter. So it's likely, what would the final relationship between delta T for both of these be? We can even calculate it based on these numbers, right? So if we found out what it was for the iron, we would take 10,000 joules, we divide by 1 kilogram, and then we divide by the specific heat, which is 470. And we would get delta T. It's basically 10,000 divided by 500, so it's going to be approximately 20? Is that right? It's about 20? Yeah, about 21. So if I tell you that delta T here is going to be 21 Kelvin, or 21 degrees Celsius, because it's change, right? So this would go to a final temperature of about 41 degrees Celsius. What do you think this one's going to go to? 910 is about twice as much as this, right? So I would say the final temperature of this should probably be something like 30 degrees. Does that make sense? Do you guys have any questions? And you can plug in numbers here if you want to get the exact answer. You get 10,000 divided by 910. Yeah, 10.98, so it would actually be closer to 31. And the way Tom put it is that it looks like it needs less energy per kilogram to heat it up. Yep. Okay, so how does this compare to water? How does this compare to water? So, oh, this is all together here. I'll just scoot it over so we can just see the water portion of it. So, when you heat water up, right? The specific heat of water, this isn't going to fit on this page. I'll just move the whole thing over here, and we'll just look at just the picture part of it. So water has a much higher specific heat than the glass or metals used in cookware. It explains why it takes several minutes to boil water on a stove, even though the pot or kettle reaches a higher temperature really quickly, right? If you put water into a pan like this, you put it on the stove, and you let it sit there for a minute, what's 21K? Was that this? Sorry, why did you say that? Oh, were you calculating it and you didn't see that we already did it, or? Okay, I'll just keep going. Maybe that was just delayed. Right. So you take a pot of, you take a big pot, you put it on the stove, you turn on the heat, you fill it with water. The water starts off at a very cool temperature. The whatever container you have it in starts off at a really cool temperature, but the container gets hot really fast. The water takes a lot longer to get hot, right? That's specific heat for you, because the specific heat of water is 4186 or 4190, basically. And that's liquid water. Notice that the specific heat of ice is different, and that's important for some stuff we'll do later. Specific heat of water is like this, and that number is pretty clearly connected to the definition of the calorie, right? You notice the value is the same. So a calorie is basically just specifically related to water. Specific heat applies to all materials. It measures the rate at which materials actually speed up. Why is it Kelvin? Oh, well, because we're talking about temperature changes, this could be Kelvin or Celsius. It doesn't matter. Doesn't matter. And the reason why it's Kelvin is probably because it's the SI unit of temperature. All right. So there's also this other equation right here, which is useful. We'll need it for the problem that we're going to do in a second. It may show up in some lab manual problems and some of the problems from the textbook as well. But for an infinitesimal temperature change dt, the corresponding quantity of heat is dq. Okay, and we get this equation that we're going to use in a problem we're going to do here in a second. dq equal to mc dt. I'm also going to mention now, because we're definitely going to be needing this later on, that there is another version of this in which you basically say that if I know what the molar mass of an object is, the number of moles or grams per mole, and I multiply that by, so what is molar mass? Molar mass is, you guys tell me. What is molar mass? What does that mean? It's kind of actually written in this little paragraph right here. It's like grams or kilograms per mole, right? Molar mass represents like the number of kilograms per mole of substance. Is it grams per mole? Well, I mean, it can be in either, right? On the periodic table, okay, maybe this is what you're thinking. On the periodic table, if you look underneath like carbon, I'll write carbon. You get some number that's like 12.011 or something like that, right? I don't know what the number is. This is definitely grams per mole. You're right about that. So molar mass, grams per mole, kilograms per mole, however you want to put it. If you then take this, right, if you take molar mass and you multiply by the number of moles, that gives you, so if n is the number of moles, which is shown, this gives you mass, right? So this can allow us to define something that's called molar heat capacity, where the molar heat capacity, we use a capital C, and it's equal to, you just replace, so before our equation was Q equal to mc delta T. You replace the m with the molar mass multiplied by n, and then you define here that molar heat capacity is the molar mass multiplied by specific heat. And then you can get this version right here. This one's kind of interesting because there's something special that happens with molar heat capacity. So it's quite literally just molar mass multiplied by specific heat. And here's an example. The molar mass of water is 0.180 kilograms per mole. You multiply by the specific heat of water, which is here, and you get about 75 joules per mole Kelvin. So this is just another way to do the calculations. And it's going to be specifically relevant when we talk about gases, because as it turns out, the molar heat capacity, that's the name that's given for it here, molar heat capacity. This is going to be something, for gases at least, that is going to depend on whether you're talking about constant volume or constant pressure. And you're going to have something called CV and something called CP, one that's going to represent molar mass for constant volume, and one that's going to represent, not molar mass, sorry, all these new words. This is going to be molar heat capacity for constant volume, and this is going to be molar heat capacity for constant pressure. So this is volume and pressure. This is when we start talking specifically about gases, this is something we're going to need to know something about. But something interesting happens when you talk about molar heat capacity. Now, this table is pretty simple. If I take column A and I multiply by column B, I get column C. Okay? Because specific heat times molar mass is molar heat capacity. That's what this says down here. Molar heat capacity is C times M, right? Or 1 over N dq dt. This type of relationship here will be useful for us later. Both parts of it. So, one thing that's interesting is if you look at the molar heat capacity here, you might notice something about some of these numbers. Do you notice anything? So look at the substances and look at the things over here. Do you notice anything? Does anything stand out to you? Does anyone see it? Okay, so Tyler noticed the liquids are higher than solids. Is that right? Let's see. Ethanol, ethylene glycol, water. Yeah. Well, marble's a little bit higher, but yeah, for the most part, these seem to be a lot higher. Water is... So ethylene glycol is actually the highest. Okay, and what did you say, Kim? Mm-hmm. So aluminum, copper, about 25. Iron, a little bit more, but close to 25. Lead, also a little bit more, but close to 25. Mercury, same thing. Silver, same thing. What's the difference between... So it's not just... Is it just metals? In this table, it's just metals. What's the difference, for example, between silver and salt? Or water and silver? Or marble, for that matter? These are compounds, right? They're not just single elements. So it seems to be the case that for elements, not always the case, but the molar heat capacity is approximately 25 joules per mole Kelvin. Which means that the kind of like, it's like the energy per atom effectively, right? The energy needed per atom to heat the object up is approximately the same for elements. Maybe just metals, I don't know. And that's not true for all of them because beryllium is very different, right? But I guess this was something that was discovered by some scientists, that the molar heat capacity seems to be about this for elemental substances. Now, the specific heats are very different because you have to multiply, right? So some of these, what's really heavy? Lead is really heavy, right? So as a result, lead being really heavy, it has a very small heat capacity compared to what's something that's light. Aluminum is really light, right? Is copper... I'd have to pull out a periodic table. Maybe someone can. How are copper and aluminum related on the periodic table? Pull up the periodic table. So copper's 29. Where's aluminum? Yeah, 13. So aluminum is extremely light. That makes sense. So aluminum is like the lowest one on here in terms of its mass, molar mass. And so as a result, it has a really high specific heat. Okay, so that's some stuff about specific heat. I want to do one problem real quick. This one's also from your textbook. This will be the last thing we do, and then we're going to stop. And for this one, we're going to need this version. So I'm going to write it down here. Can I write that right? Yeah. All right. So the problem states, you're designing an electronic circuit element made of 23 milligrams of silicon. The electric current through it adds energy at the rate of 7.4 milliwatts, which is this. If your design doesn't allow any heat transfer out of the element, at what rate does its temperature increase? The specific heat of silicon is this. What are we given on this problem? You're given mass, right? So we've got M and we've got C. Then how do we use this dq and this dt here? T is temperature, Q is heat, or energy. It says the electric current through it adds energy at the rate of 7.4 milliwatts. So what's that? What is that? What is 7.4 milliwatts? Is it dq? It's not measured in, like dq would be measured in joules. So it's not exactly right. What is watts usually? It's dq dt, exactly. So what if we divided both sides by some time interval? Then dq dt, as Ange is saying, would be that, 7.4 milliwatts. All right, our question here is, at what rate does its temperature increase? So really we want to solve for that piece right there, right? So if we write 1 over mc times dq dt, that should give us the rate at which the temperature increases. Plug everything in, 1 over and then c is this. And then we multiply by dq dt, which was 7.4 times 10 to the negative 3. You know, they had milli and milli. We could have just left them in there, I guess. And that should give us our answer. All right, so we'll calculate this. Get a really tiny number. So I get, let's see if I did this right. It's milliwatts, milligrams, yeah, okay. So I got 4.56 times 10 to the negative 4. And this would be degrees Celsius per second. That's the rate at which the temperature is increasing. Every second increasing by that amount. Given enough time, like a minute, for example, you'd have 60 times this. After an hour, the object would obviously get really, really hot. Okay. I'm going to stop there for now. If you guys have any questions, let me know.